Today's video is an introduction to our unit on chemical equilibrium. A chemical system can be described in terms of empirical properties such as temperature, pressure, volume, and the amount of substances that are present. It is easier to study systems that are separated from their surroundings by a boundary. These are called closed systems. A reaction that occurs in solution can be considered a closed system even if it is in an open beaker, as long as no gases are used or released by the reaction. If gases are involved, the container must be closed on all sides. A soft drink in a closed bottle is a chemical system at equilibrium. Nothing changes inside until the bottle is opened. When the cap is removed, the pressure changes, and so does the equilibrium state. This results in the release of carbon dioxide from the solution. For this unit, it is necessary to adjust your thinking about chemical reactions. After most reactions, there are still some reactants present. In truth, not all reactions are quantitative, meaning that not all reactions result in 100% reaction completion. This reality can be explained by the collision reaction theory. The final state of a chemical system is a result of the competition between collisions of reactants to form products and collisions to reform reactants. For this theory to hold true, the system must be closed. Examine this chemical system in equilibrium. Notice the type of arrow that is drawn between the reactants and the products. This arrow shows that some reactions are taking place in the forward direction and some reactions are taking place in the reverse direction. Any closed chemical systems with no observable changes occurring are at chemical equilibrium. There are three types of equilibrium, including phase, solubility, and chemical reaction equilibrium. All three types are explained by a theory of dynamic equilibrium. Dynamic equilibrium is when a system has a balance between two opposite processes that are occurring at the same rate. In phase equilibrium, there will be more than one phase in a closed system. In this example, the forward reaction would be the phase change from the liquid to gas state, and the reverse reaction would be a phase change from the gas to liquid state. At equilibrium, there would not be a net change in the quantities at each state because the two processes would be occurring at the same rate. In solubility equilibrium, a solute will be dissolving and crystallizing. The solution is saturated, but there is still the expectation that some of the ions will be recrystallizing and some of the crystals will be dissolving. Both processes occur at the same rate at equilibrium, so the amount of solid at the bottom of the beaker would be expected to stay the same. Chemical reaction equilibrium involves actual chemical reactions. The hydrogen iodine reaction system is commonly studied to help understand chemical reaction equilibrium. Notice how all of the entities in this sealed flask, the hydrogen, iodine, and hydrogen iodide, are in the gases. Initially, the flask only has hydrogen and iodine molecules, but as they react, the amount of hydrogen iodide increases. Eventually, the system reaches equilibrium and the numbers of each entity will stay the same, although it is known that forward and reverse reactions are still taking place. This table shows the concentrations of each entity initially and after equilibrium. Some things that you may notice here are the ratios of each entity remaining the same once the system reaches equilibrium. There are two different ways to talk about equilibrium. The first is percent reaction. It is a number that shows a percent amount for how much of the reactants are converted to products. This is calculated with stoichiometry. Another way is to use something called an equilibrium constant. Equilibrium constants are unique to every chemical system. A graph can also show the amounts of reactants and products over time. Here you can see the concentration of hydrogen and iodine decreasing while the concentration of hydrogen iodide increases. Some other things you can observe in this graph are the fact that the rates of reaction decrease as the number of reactant molecules decrease. Also, the rate of reverse reaction increases as the amount of product molecules increases. Eventually, the two rates will become equal. That point is equilibrium. The evidence from the previous table shows that the percent yield of hydrogen iodine system was 78%. When a percent reaction is determined, the percentage is written above the equilibrium arrows. Scientists believe that all reactions are occurring in forward and reverse directions. Reactions can fall into one of four categories, though. Some reactions favor the reactants, so they may react less than 1%. Some reactions favor the reactants, and a percent reaction of less than 50% is expected. Some reactions favor the products, and a percent reaction of more than 50% is expected. And finally, some reactions favor the products strongly, and a percent reaction of more than 99% is expected. These are our quantitative reactions. This table summarizes the classes of chemical reaction equilibria. Thanks for completing your introduction to chemical equilibrium. We will be reviewing each of these concepts in class tomorrow.